Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. In this episode of our Deep Learning Indaba series, we're joined by Naila Murray, Senior Research Scientist and Group Lead in the Computer Vision Group at Naver Labs Europe. Naila presented at the Indaba on computer vision. In this discussion, we explore her work on visual attention, including why visual attention is important and the trajectory of work in the field over time. We also discuss her paper, Generalized Max Pooling, and her recent research interests in learning representations with deep learning. Before we jump in, I'd like to send a big shout out to our friends at Google AI for their support of the podcast and their sponsorship of this series. Google AI recently opened up applications for their 2019 residency program. The Google AI Residency is a one-year machine learning research training program with the goal of helping individuals become successful machine learning researchers. The program seeks residents from a very diverse set of educational and professional backgrounds from all over the world. So if you think that this is something that interests you, you should definitely apply. Find out more about the program at g.co/AI residency. And now, on to the show. All right, everyone, I am on the line with Naila Murray. Naila is a senior research scientist and group lead in the Computer Vision Group at Naver Labs Europe. Naila, welcome to This Week in Machine Learning and AI.
Thanks so much, Sam. Happy to be here.
I'm happy to have you on as well. And before we jump into the kind of heart of the conversation, I'd like to have the audience get to know you a little bit. You did your PhD in Barcelona, Spain. Tell us about your focus there.
Sure. So I did my PhD at the Universitat Autònoma de Barcelona, so specifically in the Computer Vision Center in Barcelona. And so the work I did there was very focused on subjective vision. So this is the problem of being able to model subjective properties of human vision. So that's things like, in particular, I was focused on visual attention, in particular, bottom-up attention, or what we might call saliency. So this is really understanding if you're given some kind of, if an individual is presented with a visual stimulus, let's say an image or a video, how can we model which regions of that visual stimulus would attract the user's attention? And then we can have various degrees of attention that we can predict. So that was one focus of my research during my PhD. Another focus was on visual aesthetics. This is another, let's say, subjective visual experience where you're trying to model, or at least trying to understand or predict, to what degree would a specific visual stimulus, let's say an image or a video, be considered visually appealing to someone. And so you can consider different ways of approaching that. There are some that are, let's say, some approaches that are a bit more in the computational neuroscience perspective, really taking a sort of biologically inspired approach. And I did investigate that to some degree. And there are also much more data-driven approaches. So things that would be, using machine learning techniques. So I investigated both aspects during my PhD.
And during your PhD, you did a stint with Xerox Research Lab in Europe. You went there after your PhD, and without leaving, you ended up at Naver Labs Europe. Tell us about that whole story.
Sure. So it was a very interesting time. So in fact, I was a visiting researcher at Xerox Research Center Europe, XRCE, for those in the know, during my PhD. So actually, I was visiting them and collaborating with them as a PhD student. So after my PhD, I had a great time at XRCE, and so I decided to stay on as a research scientist. And eventually, I started leading the computer vision team at XRCE. And at a certain point last year, Xerox decided to transition, and we were looking for acquirers for the lab. And so Naver Labs, and so I can get in a little bit into what, who are we as Naver Labs? Naver Labs acquired us eventually, acquired XRCE. And so now XRCE is now known as NLE, or Naver Labs Europe. And so the institute is the same, the people are the same, but now we're under the umbrella of our new home, which is Naver Labs.
And Naver Labs does what?
Okay, so this is like an onion and an onion story. Um, let me start off with Naver Corporation. So our parent company is Naver Corporation, and this is a South Korean internet technology company. We're a very dominant company in South Korea, and then and for different services in other parts of South and Southeast Asia and East Asia. So we're very well known. We're very dominant in search, for example, in web search and mobile search in South Korea, and then we have many other services. We have a lot of internet and web services for things like for translation, for navigation, for maps, for blogging. We have more than 100 services that we provide over the web, over the internet, over mobile phones. We also we own Line Corporation, for example, which is a very popular messaging app as well. So this is Naver Corporation, and so Naver Labs is actually a spin-off of Naver Corporation. And so Naver Labs, what we are is we're a company with a vision of ambient intelligence. So what this means is we are interested in having services that are intelligent and that that take context into account when it's deciding how to best provide some kind of service. So that might mean understanding where you are, understanding what you're doing, and using that to provide you different services related to, for example, mobility or entertainment or communications, things like that. So that's the vision of Naver Labs. And as a result of that, we do a lot of research on things like computer vision, natural language processing, recommendation systems, a lot of machine learning tasks in general, and also applications like robotics, autonomous driving, and quite a few other things.
You recently returned from the Deep Learning Indaba, and in fact, this interview will be published as part of our Deep Learning Indaba series, where you presented an overview, a tutorial on CNNs. I'm curious about your experience at the Indaba. Had you been to the Indaba event previously? And tell me a little bit about your experience there.
Sure. So I hadn't been previously. As far as I understand, this is the second edition of the Deep Learning Indaba, and I wasn't there last year. I was really happy to be invited to give this overview of convolutional models, and I have to say it was really a great experience, on all dimensions. So in terms of the organization, it was great. In terms of the group of students and participants that the organizers put together, they were really a very engaged, motivated audience. I was you never know when you're giving a talk how engaged the audience is going to be. We got so many questions during the talk, which is always great. After the talk, a lot of questions as well. A lot of students coming up to me afterwards saying, oh, I saw this, you spoke about this specific kind of flavor of a ConfNet. Do you think it could be used in my case? Here's what I'm trying to do. So people are really, really willing to explain, to describe their problems, to look for advice, to ask questions, to share knowledge. So I thought the general spirit of the DL Indaba was great. It was really, I think, in the best spirit of conferences, in the sense that people are really there to share knowledge and to find collaborations and things like that. So it was a very nice spirit. I think I also learned a lot listening to some of the other talks. They were great talks by people like Katja Hoffman and David Silver and others, many others, where I learned quite a bit of stuff myself too. So in all, it was really wonderful.
Oh, fantastic. And so your recent work has been focused on areas like visual attention and learning different representations for visual search. Let's dive into some of your recent research. Visual attention. When we talk about visual attention, is it related at all to, we talk about attention within models. What are the connections between those, or is it just a name collision?
Sure. So that's a great question. I would say there's an intersection, but it's not a complete overlap. So visual attention has a very specific meaning in the neuroscience community and in other communities, right? It's not something that computer vision people came up with. But there is some overlap. Basically, when I say visual attention in the context of my research, what I really mean is human attention that's, let's say, that's given or that's a result of the human visual system. And you can think of even higher up visual processes and cognitive processes. The idea being that, so for example, to give you a typical setup, in terms of what we're trying to model, let's say, for example, that you sit somebody in front of like a computer screen, you show them an image, and then you have an eye tracker, and the eye tracker is tracking exactly where fixations are landing on that image, right? And the goal of a visual attention model will be to predict that, to be able to say, given this image, I think that, let's say, the average person, because of course there's a lot of subjectivity that goes into this, but the average person would pay more attention to this part or to that part, or I think that part's going to gather a fair bit of attention, or this is the degree to which I think it would have that amount of attention. So that's what I mean when I say visual attention, and that's the type of research I did. But in a lot of CNNs now, and let's say general deep learning models, it's used in a very similar sense. The idea being that, but it's not necessarily human driven, right? It's basically saying, what does the algorithm, what does the model basically think needs to be attended to in whatever stimulus you're talking about. And that can be a visual stimulus, it can be textual data, it can be many other things. So it's not necessarily human driven, but the concept is similar in the sense that there's a lot of information. What information is relevant for me to make whatever decision I'm trying to make?
Why do we want to study visual attention? Yeah, you could step back and think about it as, more like a bug than a feature, or a limitation than a feature, right? It's like we as humans have this limited ability to focus due to a variety of kind of neurophysical, limitations, the way we're wired. But a computer could do more, right? Why do we need to worry about focusing on a specific part of an image?
You could say that, but I actually think that visual attention is kind of a miracle. I wouldn't say it's a miracle, but it's actually a very wonderful feature of the human, let's say, human cognition, in the sense that there is a vast amount of information that we're taking in every time we just look around us, right? Every time we look around us, every time we see. If you think of the amount of data that you need to store to store like an hour of video, and just imagine that we're just like having this be input into our eyes constantly, as when we're awake and when we're looking around, there's a lot of information. And it's not, rather than think that, okay, it'd be great if we could use all of this, frankly, I mean, it's very smart for our visual system to say, a lot of this is not even necessary. Why would I waste my time? Why would I have waste the energy of my brain to process this stuff that's not even needed for whatever kind of task I'm trying to do? The human brain is very computationally efficient. And that's something that we struggle a lot with in computation, especially in deep learning right now. And so I think it's actually something very fascinating and something that we would love to be able to replicate in, let's say, machines and in computer systems as well. So that's just to start off with. I find it really fascinating, the ability we have to be able to really attend to things that matter. So that's one reason why I think it's interesting, because if we could replicate that, I think it would service a lot of computational power and many other things, right? We know that right now, for example, there's a lot of issues with environmental concerns, for example, like how do you cool all these GPUs that we're all using and things like this. So if we could manage to replicate that, that'd actually be pretty cool. And then, so another reason we're interested in it is just for purely, let's say, scientific purpose, to really understand how the brain works. So that's one thing. And actually, a lot of this research came out of the neuroscience community, right? Like people who really want to understand, how does your brain work? That's just a fundamental question. And attention is a big part of that. Not just visual attention, but also attention to audio signals. And then also just for computational reasons, I just gave you a few, right? So it's really good for compression purposes and for just general computational efficiency.
Can you scope out the landscape of visual attention? What's the research trajectory been in this field over time? It sounds like it's been something we've been looking at for a long time from the perspective of multiple disciplines. How is our understanding of how to replicate visual attention in machines evolved over time?
Sure. So yeah, I can try to take you through a very brief overview. So visual attention, let's say computational models have been around for many, many decades. There are some very seminal ones. So for example, there's one by Treisman et al., which is related to what we call feature integration theory. And then from there have been some works by professors such as Laurent Ety and a lot of his students who've worked on things like really taking an image and trying to decompose that image into some sort of compressed representation. The idea being that if you have an image, there's a lot of redundancy in images, right? We all know that. So images can be very highly compressed, and anybody who's used, JPEG compression or any other types of compression techniques know that. And the idea is that there's been a long history of work thinking about the fact that to understand visual attention, we have to think about what can be compressed and what cannot be in order to retain the same information in the image. So that's been like a big theme throughout a lot of visual attention research. In early days, let's say, a lot of things was very much focused on trying to come up with, let's say, from first principles of neuroscience about, for example, how the brain works, how the visual cortex works, how the primary cortex works, etc. Trying to, from that, come up with a model. More recently, people have gone into very much data-driven approaches. So by data-driven, I mean things like, you have some sort of data set that you collect. So a typical data set that is used in this field is a data set of images and corresponding fixations from different individuals, different viewers. And a data-driven approach would basically say, okay, I have some sort of model, and this model can be a deep learning model, it can be some other type of model, and I want to optimize this model such that it's able to predict as best as possible these fixations. So basically to give some sort of, for example, a probability score for a given pixel, saying what's the probability that a fixation would land on that pixel. So a lot of work on this field has used things like image decomposition methods, for example, using wavelet theory, using wavelet decompositions. More recently, it's gone, a lot of the research has gone into deep learning. So, for example, some of the recent research that I did used a very generic, let's say, visual backbone, you can say, a visual front end. So, for example, a ResNet model. And then, for example, train the ResNet model architecture with a final layer that gives you a prediction on a per pixel basis, saying, okay, given this image, what's the probability of this pixel being fixated upon?
And so your specific work in this field, what were some of the papers that you've done in this area?
So the first work I did on this, so this was before the deep learning era, if we can put it that way, was really based on using a psychophysical model of vision. So this model was really a model that was developed initially to predict color perception. So how do we perceive color in images? And then we adapted this model to predict visual attention, more specifically saliency. So maybe before I get into this, I can give a little bit of a distinction between the two things. So when we talk about visual attention, this is something that's an extremely complex, let's say, process in cognition. It involves many, let's say, what we might call low-level cues and also many top-down cues. By that, what I mean is that typically when you're looking around you and you're paying attention to things, you have some sort of purpose in mind. So, for example, you might be reading, or you might be looking at a movie, or you might be searching for something on your desk. And that impacts a lot where you look. So this is why it's very subjective. So there is a component of attention, though, that's been traditionally called saliency, and this is something that people call more bottom up. So what that means is it's something that's more related to things like textures, like low-level textures and colors, and things that aren't really related to the task at hand. So what I mean by that, for example, is even though you're looking at your desk and you're trying to find something, there are certain things that are just, let's say, fundamentally salient, for lack of a better word, in your desk. So there are many patterns that have been found that have this property. And so this was more what I was focused on, this aspect of really a bottom-up saliency or low-level saliency.
Is it fair to draw this distinction along the lines of bottom-up or saliency is specific to the content of, let's say, an image, whereas top-down is more contextual or related to the goal of the observer? Or is that too simple?
Yeah, I think that's a fair distinction to make. Exactly. Okay. Yeah. So we would say that, and this is why I think if you're trying to model attention, many people have started off trying to model what we call bottom up or low level attention, because that's the sort of thing that's really it's less task dependent, right? It's really sort of depends on just the fundamentals of the visual stimulus that you have, and so that way is a bit more. There's a bit more continuity of that or coherence in between different viewers. When you start to get into things like looking at different tasks, it can be very subjective and very different.
So your specific research was taking a kind of a neurophysical model. Is that how you described it? Approach?
Right. Yeah. So that was my initial work on this, which took a psychophysical model and it attempted to modify it to better predict let's say visual saliency, and in particular to predict visual fixation, so eye fixations. So what that meant is that you take a data set with these fixations that were recorded by different observers, and you try to really replicate that with your model. So later on, in more recent years, I've looked at a more data-driven approach with some learning involved. So in this case, what we did was we really focused on. So this is work I did with a student of mine, Samia Jetli, and also a colleague of mine, Nora Vig. And so for this work, we focused on really trying to understand what kind of objective functions would be appropriate to learn a model of saliency. And so we modeled saliency as a probability distribution. So we said, okay, we want to really predict the probability of fixation. So we consider all our pixels in our image to be potential fixations, and we try to figure out, okay, what would be like the best objective function to learn to train this model. And so we consider different ones. We propose some new ones, basically, that we're trying to really capture this property of probability.
And so what were the field of objective functions that you considered?
So very much those related to capturing differences between, or let's say to quantify differences between probability distributions. So for example, we try things like Kale divergences, Jensen-Shannon differences, chi divergences, and then many others. And so then basically we finally proposed like an objective function that's basically a combination of a softmax function, which allows you to have a valid probability distribution, then to apply different types of divergences, probability divergences on top of that. And we found that worked quite well. And in fact, we found that the Bhattacharya distance worked quite well.
The what distance?
So there's this, it's called the Bhattacharya distance. It's quite well known. It's been used in many fields. I think it could be used more actually than it is right now. But actually, the Kale divergence actually works also very well. We compared several ones, and then we found that these two were pretty good.
So in the case of, I'm trying to map this to like simple Gaussian type distributions where translating from one to the other is related to kind of the mean and the variance. Do those correspond one-to-one to terms in these different functions?
No, so these are very generic. So basically, they're not necessarily some sort of generative model, for example. It's really, you assume that you have, for every value you have in your distribution, you're assuming that you know what the value is, right? So you have like probability of x1, probability of x2, etc. So that can be modeled, for example, with a GMM or with something else, but this is sort of agnostic to that. These types of distances, they're saying once you have some sort of probability distribution, this distance is going to compute the difference between the two, but they can be modeled differently.
All right. And so how do you use this ability to compute the distance between two distributions to help you figure out attention?
So what we start off with, so our ground truth can be converted into a probability distribution. And this is what we did. And we're not the first people to do this, but this is something that's very that has been done before. So for example, you start off with a set of fixations. So you can consider that you have an image, and you know the XY coordinates of where somebody fixated on that image.
Does your data set consist of one image and a large number of captured fixations from different observers based against that same image, or do you have a bunch of images, each with their corresponding fixations?
So both. So we have multiple images. Ideally, in the beginning, we had very small data sets, but now we have pretty big ones. So you have multiple images, and for each image, you have multiple sets of fixation. So basically, for example, you might have like an image, and you ask like 10 people to take a look at the image, during a very small amount of time. So maybe like up to 2 seconds. And so then you capture these fixations. And normally what people do is they apply like Gaussian blurring to that. So you can imagine you have like an image which is full of zeros. And let's say you have like ones at the locations of the fixations. And then you can apply Gaussian blurring to this. And what you're going to get is this resultant image which is diffuse, right? So you have high values at the fixation points. And then these high values sort of diffuse in the immediate area of the fixation. So what you end up with is sort of like it's not sort of like a binary image, but you have some diffuse attention around the regions of fixation, with the modes being at the fixation points. And so this can be what you have now is rather than have like an image full of zeros with a few, with just a few points where there's some support of the distribution, now you've diffused a distribution where you have basically some amount of non-zero support at all points. And if you normalize this resultant image appropriately, you can consider this image to be a probability distribution. And so then this becomes your ground truth. And you just apply your typical machine learning framework and you say, okay, this is my ground truth. I have a model that takes as input an image and produces some sort of predicted distribution. And then I compare the two using my probability distribution, my difference measure, and you backpropagate the loss, right? You backpropagate the difference that you see.
And so why is that diffusion step key here as opposed to the more binary approach of looking at the fixations?
It's as we have a somewhat subjective process. It's a little bit too strict of a task to ask the model to predict exactly the fixation point, because you could imagine that the user could have very easily looked elsewhere, and you can actually see this, right? Because if two observers are looking at the same image, they're not going to look at the exact same point. So therefore, if you have a location, so for example, you have an image and there's it's an image that contains a face. Very likely there's going to be a ton of attention paid to the face. People like to look at faces, but they're not going to look at the same points. Not everybody's going to focus exactly on the eye, right? So if you have 10 people, you might see like a distribution of fixations very much on the face. But you can imagine very easily if you had like another person, if you had an 11th person that looked, they might look not exactly on that point, right? But they would look in the general area. So this is why it's nice to not use just the actual fixation that you have, but to sort of do this diffusion process where you basically apply Gaussians to those regions and have this diffused distribution.
And you're doing this diffusion process to each of your fixation images, if you will, as opposed to after aggregating or averaging across the different fixations for a particular image?
Exactly. I mean, there are many different ways to do this. You can imagine. I think you can see that there are different choices, right? And none of them are exactly correct, right?
Right.
So in this case, we're trying to solve like a pseudo problem, like an adjacent problem, because we're not actually solving the exact one, right? Because this is where the subjectivity of it comes into play. So yeah, there are different ways of doing it, and of course, there's when you're applying sort of this Gaussian blurring. The Gaussian filter itself has its own parameters, right? So you have to decide how diffuse do you want this to be, and that itself is a question that's sort of left up to the specific researcher.
And do you, in that sense, it's not something you're learning; it's a hyperparameter that you're choosing via experimentation?
It's not even a hyperparameter, because this is really the ground truth you're setting at this point. So really, what many people have tried to do is to set this in a somewhat principled way by trying to look at things like peripheral vision and trying to understand, okay, if someone actually fixates, how localized is that fixation really? And then you can kind of have a measure on what sort of local region is really being attended to. Okay. And there's a lot of psychophysical studies on that, and that can inform how diffuse you want this to be.
And so that's. Are we just finishing up your first work in this in this field?
It sounds like it. Yeah, we have a bit more to cover.
So where'd you go next?
Some of this work was done actually while I was at XRC, now NLE. Some other work I've done while here is related to, as I said, learning visual representations. So I also did a fair bit of work on this once again before the deep learning era. So this was using handcrafted features and trying to understand how to learn embeddings in an effective way for different tasks. So things like fine grained recognition and also visual retrieval. So maybe I can start off with some of the work I did recently with colleagues from INRIA and also colleagues here at NLE related to what we call aggregation. So this is also something that has become very well known in the deep learning context. And what I mean by that in particular is, for example, what is something people very often refer to the same sort of principle as pooling. So, for example, average
like
pooling
max
or
pooling
max pooling, exactly. This is quite well known, right? So this is basically saying you have some amount of it local information, or maybe even not very localized information, and you want to be able to summarize it somehow, right? And very often, what you want to summarize might be different vectors. So let's say you have a set of vectors and you want to summarize them. So, for example, in the deep learning context, if you think of like a feature like a hypercolumn, and you want to summarize that in some way, or to, let's say, compress the information, you might use max pooling or average pooling.
Now, you referred to a feature as a hypercolumn, and I haven't heard that reference before. What does that mean?
So when I say hypercolumn, this is sort of it sounds a bit old school now. It's a term that comes from neuroscience once again, and it refers basically to it's what you might call this typical feature tensor that you find in many conv nets, where you have, for example, you have an input image and you're applying different convolutions to it. Very often, you end up at some intermediate point with with multiple feature maps, right? So you have like a feature map of size like H prime, W prime, and that's your feature map, and you have multiple ones of them, right? Let's say you have D feature maps. So in the end, what you end up with is a tensor that's like D by H prime by W prime, and this has often been referred to as a hypercolumn.
Okay.
So that's in the deep learning context, but you can think of many contexts where you have feature vectors that you want to summarize in some way. So, for example, in my work, we worked a lot with what we call Fisher vectors, and so Fisher vectors are it's a type of representation of visual content, particularly used a lot with what we call local descriptors. And so it's a way of basically saying, okay, I have some local region of an image, and I want to find some vector representation of that local region that's discriminative and compact, hopefully. Okay, and so imagine you have an image and you have a set of these descriptors that you extracted, let's say, for different regions of the image. And you say, okay, I have this image, I have, I don't know, like n of these descriptors, and I don't want n, I want like fewer. I want maybe one, or I want two. So the idea is, how do I go from that n to that much smaller number while not losing too much information? So this is like a fundamental problem that has been tackled in many ways. And so I've done some work on how to construct these, what we call aggregated representations, from a set of like a larger number of them.
It sounds like, and you mentioned the term embedding previously. It sounds like you're creating some embedding space and then doing something akin to dimensionality reduction on that embedding space.
So it's not quite in the sense that when people talk about dimensionality reduction, typically they mean that you have an embedding space, right? Mm-hmm. It can be in, let's say, D dimensions. So, for example, I don't know, 2,000 dimensions. And for dimensionality reduction, what you want to try to do is find some smaller dimensional space in which your embeddings live. So, for example, I don't know, you might want to go down from 2,000 dimensions to maybe 500 or 256 or something like this. Mm-hmm. In our case, what we're doing is we're not changing the embedding space, but we're just changing the amount of samples from that space. Let's say the amount of vectors that live in that space. So, for example, rather than have let's say 1,000 vectors, each of dimension 2K, you might want to have only one. So this is what this aggregation is about.
Is that a typical example, going from 2,000 to 1?
You can go even higher than that. Yeah. So very often you might find on the order of anywhere from like 1,000 to 10,000 vectors that you want to reduce to just one vector. So you can see there that you can see
what is that doing for
difficult.
You? Yeah, what is that?
Compression. It's you're reducing the size of your image representation by a factor of the number of descriptors that you have. If you go down to one.
I guess if I'm thinking of it in the sense of compression, then certainly we'd want to do that. But I would imagine there's a tremendous amount of loss in a scenario like that. But when I think about it from the perspective of like an embedding space, I mean, I guess it's also lost. Like you just lose a ton of information. And so maybe I'm asking you to convince me that you're left with something of utility after you do this 10,000 to 1 reduction.
Sure. So you're definitely right in the sense that they both they have like an effect of compression. Right, that's for sure. Mm-hmm. In one case, you're going to a smaller dimensional space. In another case, you're just reducing the amount of representations you have. In both cases, you're losing information, that's for sure. And this was the point of my work. So my work was really on how to represent how to perform this aggregation while maintaining as much as possible, as much information as you can in this aggregated representation. So what we proposed was a method called Generalized Max Pooling, which aimed to sort of maintain this property. And of course, it's not perfect, but we found that it gave pretty interesting results over other techniques, for example, like average pooling or max pooling. And so the benefit there is once again, it's in terms of compression, which is important. So in many applications, you can't afford to store, for example, 10,000 descriptors to represent an image. To give an example, so we're very interested in my research center on the problem of image search, right? So let's say, for example, you have a database of images, let's say 1 billion images, right? And you have some image that you want to match to that. And you can think of many applications. You can think of, for example, shopping. Let's say you want to find you have an image of like some kind of clothing item and you want to find in a huge, let's say, catalog by multiple retailers, anybody who has something similar or who has the exact same one. If you have to compute the similarity between that image and all the images in that database, and each image is represented by 10,000 vectors, each of which has a dimension of 2,000, it's going to take forever. Mm-hmm. It's not practical. So this is why very often people work on how do I get from 10,000 vectors to 1 or some smaller number, somewhat smaller number. So this is really the utility there. It's a compression utility.
You mentioned this algorithm is generalized max pooling. Are you taking kind of an off-the-shelf CNN architecture, ResNet, for example, and kind of swapping out, wherever it says max pooling with this generalized max pooling and maybe chopping off the last layer, your classifier, and that's creating your vectors, or is it more involved than that?
So that would make sense. That's a good guess. But but actually, and this is something that could technically be done, but actually what we think of this is something that's very generic. So it's actually not related to it's not specific to deep architectures. It's very generic in the sense that we are trying to solve the problem where we have a set of vectors and we want to aggregate them in some way. And so that can involve features extracted by deep networks. So let's say, for example, you have a deep network and at some point you have this hypercolumn I talked about, you have this feature tensor, and you want to pool it in some way, you want to aggregate it. So you can think of generalized max pooling in this scenario as an alternative to max pooling or average pooling. But you can also have other descriptors, right? So you can have descriptors that are handcrafted or come from many different things you can think of.
It's more presented as a fundamental operation you can apply to a set of vectors to aggregate them, as opposed to something that's specifically used in the context of a deep learning model.
Exactly. Yeah. And in fact, in the original work, we didn't apply it on deep learning, although it's been subsequently used with deep models in combination.
And so you've spent this time on the visual attention side. It sounds like that was a bit earlier in your research. More recently, you're working on learning these representations. Where are you headed? What's kind of interesting for you nowadays, and where are you investing your resources in terms of future research?
Sure. So actually, everything sort of all becomes new again. So actually, I'm doing some work now on both things at the same time, because as you mentioned very presciently before, attention is it's used everywhere, right? In deep learning right now, in many things. So actually right now, some of the work I'm really involved in at the moment involves how to learn representations using deep learning with attention involved as well. So meaning how do you use some sort of attention mechanisms in order to pay attention to regions of an image that you really need to focus on in order to solve your task, right? So this is where, once again, this is like the overlap between the two views, let's say, of attention. Mm-hmm. Because once again, there's limited processing power. There's a lot of information images, and so it pays to really only spend time computing over data that's valuable. And then not only that, but it also can be considered some sort of cleaning mechanism, for example, because you can have a lot of things that that you can that might be important, but can also be just distracting and can be considered clutter, basically. So let's say, for example, you're doing, once again, let's look at the fashion example. Let's say you want to learn a representation for visual search, right? Let's use my previous example. And you want to search for, you're looking for shirts. If you have an image, there are many parts of the image that are just not going to help you find, whether these two images match, right? Whether they both have the same shirt. So you might want to only attend to the regions of the image that are relevant for that. So of course, like if you might want to pay attention to the upper body of the person, so you might want to be able to find, okay, where is the upper body of this person? Because this is where I'm going to really be able to tell if there's a shirt in the image, and if so, if it's the same shirt, if it's the shirt I'm looking for. Now, there might be other parts of the image that are also useful for that. So maybe, for example, if I find the head, I might have a better chance of finding the body, but there are many parts that may not be, right? So what I'm focused on right now is how to incorporate different models of saliency, or let's say different ways of attending to regions, so that you can simplify these tasks of learning representations for search.
Naila, thanks so much for taking the time to chat with us. It's really interesting work, and I'm excited to get to learn a bit about what you're up to.
Thanks so much, Sam. It was really great to have this conversation.
All right, everyone, that's our show for today. For more information on Naila or any of the topics covered in this episode, head on over to twimlai.com/talk/190. For more information on the entire Deep Learning Indaba podcast series, visit twimlai.com/indaba2018. Thanks again to Google for their sponsorship of this series. Be sure to check out the 2019 AI Residency program at g.co/AI Residency. As always, thanks so much for listening, and catch you next time.